This video will cover section 11.4, geometric series. We have three objectives. We will find the sums of geometric series. We will then use that same formula to solve for specific terms of a geometric series, and then we'll finish with application problems. So let's start by defining a geometric series. Just like arithmetic series, a geometric series is simply the sum of a geometric sequence. Take any sequence, add it together, that becomes a series. So we're going to take geometric sequences and add them together. So let's look at an example of what this might look like in an application. Suppose you email a joke to 3 friends on Monday. So this is you here. You read a joke, you thought it was funny, you sent it to 3 of your friends. And let's say that each of them thought it was equally funny and they sent it to 3 friends as well. So on Tuesday, these are all the new people that have read it. And if you count up all the dots that I've circled, that would be the total number of people that have read it by Tuesday. And then let's say this pattern continues. So each of those people that read it on Tuesday, they tell 3 of their friends, and that pattern just continues. This is a visual representation of what a geometric series would look like. So these are the individual days. So on day 1, which would have been Sunday, you read the joke, and then the next day, 3 additional people, and then 9 additional people. So each of the numbers just represents each day after that how many new people have read the joke. Now we're going to be looking at this itself is the indicated sum, but we're looking at trying to actually evaluate the sum. If you add all those numbers up, you get 3,280. But it would be a pain to add each individual term. So we saw this same type of thing with arithmetic sequences and series as well. So remember, just to recap, the explicit formula for an arithmetic sequence was the nth term was a1, the first term, plus n minus 1 times d, where d was the common difference. So that would just tell you an individual term. It would tell you that term there. Then we came up with a formula that added all the terms up, meaning it would have told you this term. And that formula was denoted by S sub n, and we had 2 forms for it. I'll just write one of them, the easy one, which is n over 2 times a1 plus a sub n. You added the first and the last term together, multiplied it by n, and divided it by 2. That would give you this number, provided that the series was arithmetic. So for geometric, we already came up with the individual explicit formula, meaning the corresponding formula for this was a sub n equals a1 r to the n minus 1. This gave you the nth term. Just like this gives you the nth term, this one gave you the nth term. So the question is, what is the formula for the sum of all those terms? So we're going to go straight to the answer. I've typed it up here as a theorem. It says if a sub n is a geometric sequence where a1 is the first term and the common ratio is r, like it's been, then the sum, we're going to still denote that by S sub n, use the same notation. This is what the sum of a geometric sequence looks like. That's nothing new. We know that's what a geometric series is. And then this is just expressed as summation notation. So really nothing new between each of these. The important part of this is right here. This is the closed formula. The sum of a geometric series is the first term multiplied by 1 minus r to the n over 1 minus r. So to show you what I mean, let's go back to that previous example and apply it here. So the formula that we just claimed is true is that the sum will be the first term multiplied by 1 minus the common ratio raised to the nth power divided by 1 minus r. So in this particular example, the first term is 1, and then we'd have 1 minus the common ratio is what are we multiplying by each time. So you can see that we're multiplying by 3 to progress through this geometric sequence. So it would be 3, and then how many terms did we have? 1, 2, 3, 4, 5, 6, 7, 8. So total of 8 terms, and then it'd be 1 minus 3 on the bottom. If you evaluate this using a calculator, you should get this same value. So let's actually test that. So if I can keep all of this up here. Okay, so we had 1 times, which you don't really need that, but put in your fraction. Remember, if you don't remember how to get the fraction, you have a couple options. You can press alpha and then F1. Notice this is green, and you have the green F1 here. That brings up your shortcut, and then the very first option there is your fraction. If you have the newer operating system on your calculator, then you can just press alpha X, this alpha and then the variable button, and that brings up the fraction. So then 1 minus 3 raised to the 8th power over 1 minus 3. And we get that value. So we can bring that over, and you can see that indeed we're getting the same answer as this here. So it enabled us to add all those terms up without manually doing it. So it's still a messy computation, but it's quicker than typing in all of those numbers. Okay, so it appears to work, but we should prove in general why it actually works. So I've got the proof already typed out here for us. So let's go through it. So I'm saying let S sub n be this geometric series, just a standard geometric series. I've rewritten it here. And then below it, I wrote the series again, but I'm going to multiply it by r. I'm multiplying every term in here by r. So imagine just coming back and let me use red here. Multiply that by r. If I multiply this by r, it's going to become r squared. Multiply this by r, it becomes r cubed. Everything gets multiplied by r, which means this last term, if I multiplied it by r, you're going to add the exponent, and the exponent is just going to become n. So what ends up happening is it kind of shifts all these terms over, right? If you multiplied everything by r, you're going to get this expression here. Okay, now I've just lined them up so that the like terms, the matching terms, are underneath each other. Now, this bottom one has no just a1 term because the first term was multiplied by r, so it got shifted over here. So there's nothing to line up under that one. And then similarly, the last term became a1 r to the n, and there's nothing above to match up with that. Okay, so then what we're going to do is we're going to subtract down. We're going to take this minus this. So I've just written that there, s sub n minus r times s sub n. These aren't like terms, so I can't do anything with that. And when we subtract down on this side, there's nothing to subtract from this, so it survives right here. But these cancel when you subtract, those cancel, the next one would cancel, and they keep canceling all the way down until you get to the last one. There is nothing here to cancel it. Now really what we have there is a 0 plus 0, so we have 0 minus this term, which is why it comes out as negative here. So the only thing that survives this difference is this first term and this last term on the bottom. Okay, so we get this result. The next thing that we do is we have like terms on each side. S sub n is a common factor, I should say. We can factor that out, leaving 1 minus r here, and then I can factor a sub 1 out on this side, which leaves 1 minus r to the n. The goal was to get this thing by itself, so all we're going to do is divide both sides by the 1 minus r. Just divide that over, and that gives you this expression here. And this is equivalent to what you have here. This having the a1 in the numerator is the same as just having it out in front. So you will see this formula in a lot of textbooks. I think it's just easier to have it sitting out in front of the fraction, so I will typically stick with this. But that gives us an algebraic proof as to why that is the closed form for the sum of a geometric series. All right, let's try applying it again. So we've got a geometric series here. It says find the sum of the first 10 terms. Let's write down the things that we know. We know the first term. The first term is 16. We can find r by doing the ratio of two consecutive terms. So negative 48 over 16, that comes out to negative 3. Right? We're multiplying by negative 3 to progress through the sequence. We also know the value of n is supposed to be 10 terms. So then we go to the formula. S sub n is a1 times 1 minus r to the n over 1 minus r. In this case, we're doing the sum of the first 10 terms. I'll go ahead and put a1 in, which is 16, times 1 minus, and we end up with, what is that? Now, we got to be careful here. Put your base, that r value in parentheses, since it is negative there, and then 1 minus negative 3 in the bottom. You can put this one in parentheses as well. It's not critical in the bottom because there will only ever be a power of 1 here. It is critical to have the parentheses around that negative 3 in the numerator though. Okay, the math gets pretty messy here, so I would not require you to simplify any of that. I would just have you go straight to your calculator, and you are definitely going to want to do this with a calculator. All right, so we end up with, let's make that a little smaller. If I shrink this down, hopefully you can still see the keys here. All right, I don't think I'm going to be able to get both of them on there, so let's just type it in here. So we had 16 times 1 minus, in parentheses, -3 to the 10th power over 1 minus -3. So we end up with this number here. So that is our solution right there. That is our final answer for that one. All right, so I'm not going to copy that over, but you can see the numbers get pretty big for these answers. So don't be surprised if you see things that are quite large or quite small. So again, what we found there is if you continued this series out, wrote 10 full terms, added up all of those terms, this would be the sum of all those terms. All right, let's try a different one. This one first says, express the geometric series with the given values using summation notation, and then evaluate the series. Okay, so we haven't done a lot with this recently, so you might be confused, but anytime you have a series, the series can always be expressed like this. Oh, just sent my phone off. Okay, so when you're summing a series, then the index is going to start at 1, and you have a generator, whatever the formula is for the nth term. And then you go up to however many terms you have, which in this case is 9. So for any sequence, this would be how you write the sum of the first 9 terms. But we know that this is geometric, and geometric, we have a formula for the nth term. It would be a1 r to the n minus 1 there. That's what generates a geometric sequence. So it looks like this. Now we can just plug everything in. So this is the sum of a1 is 4, the r value is 0.5, and then leave the n minus 1 because that's going to be generated by the index here, and up to 9. So this is the summation notation or sigma notation for this geometric series. Okay, then it says evaluate it. So we want to know, what does this actually equal? Well, that's where I would go back to the closed formula we had before. So S sub n is a1 multiplied by 1 minus r to the n over 1 minus r. And so for this problem, it is the sum of the first 9 terms. And a1 is 4. And then we have 1 minus 0.5 to the 9th power divided by 1 minus 0.5. And you could go straight to your calculator for that. And provided I typed that in correctly, it comes out, it's messy. Actually, let's do this one on your calculator because I want to show you how you can convert it. Okay, so we have 4 times 1 minus 0.5 raised to the 9th power over 1 minus 0.5. If you want to go ahead and simplify that denominator, you can, but it's not too messy to just type it there. Okay, so I think I typed that in right. Okay, so if the fraction is not too bad, and this is actually not matching my notes, so if the decimal is not too bad, it should convert it for you if you just type math and then convert to fraction. All right, so there you go. So that converts it for us. So if you needed the exact value, you could just write 511 over 64. So that's what the final value should be. 511 over 64. And that's the same as this thing up here as well. Okay, so that's summation notation, and again, just applying that closed form. Okay, let's do a couple more of those. So these are given to you in summation notation, and you just need to apply the SN formula to them. So really, we shouldn't even have to tell you that this is geometric. You should be able to look at this and recognize that it matches the structure of the sum of a1 times r to the, in this case, m minus 1, where m equals 1 up to whatever the last value is, which is 7 in this case. You can see that it's geometric. That means that this is a1, and the 5 has to be your r. Now, you need to be careful with that because I could write it in a way where that's not true. The first thing that has to be true is this has to start at 1, and the exponent has to be m minus 1, or whatever the index is, minus 1. Then you can definitely say this is a1 and this is r. If you didn't remember any of that, then we could still identify those as being a1 and r. So the way you would do it is you'd say, okay, I want to generate the first term. You get that by plugging 1 in. So it would be 4 times 5 to the first minus 5 to the 1 minus 1, which is 4 times 5 to the 0. And we know 0 power on that 5 is going to make it a 1. This is really 4 times 1, which is 4. So you can get a1 just by plugging the index of 1 in. So then you might say, well, how do I get r? Well, go ahead and find a2. a2 would be 4 times 5 raised to the 2 minus 1. In other words, that's just 4 times 5 to the first, which is 20. We know that r is the ratio of two consecutive terms. So r should be a2 over a1. It should be 20 over 4, which is 5. So you can just use the regular definition to find these as well. But it's going to be quicker if you can look at this and recognize that that is a geometric series. Okay, so now we can go to the Sn formula, which again, a1 times 1 minus r to the n over 1 minus r. I guess we should have identified n over here. N is how many terms there are. It goes from 1 up to 7, so there are 7 terms. Okay, a1 is 4 times, we got 1 minus 5 raised to the 7th over 1 minus 5. All right, let's skip using the calculator. Hopefully my notes are accurate here. I got, I believe, 78,124 when I entered that in the calculator. So when you're doing this work, I'm always going to want to see this because that's where you're going to get the majority of your credit. And then, this will just be checking, can you enter it in the calculator correctly going from here to here. Okay, let's try a second one of these. So on this one, let's go straight to the values. We know a1 is 2. We know r is negative 4. Right? This is the a1, and this has to be the r. The thing that's raised to the power has to be the common ratio. We know n, the total number of terms that we're adding up, is 10 in this. It goes from 1 to 10. And then we can go straight to the S formula, which again, a1 times 1 minus r to the n over 1 minus r. So S sub 10 will be 2 times 1 minus, now be careful here, that negative has to be in parentheses. That's raised to the 10th power over 1 minus a negative 4. It doesn't in the bottom, but it does in the top. So, and that's because this even power is going to end up canceling that negative in the inside. We could actually simplify this. We could go ahead and wipe that negative in the top out. So it's really equivalent to this, and in the bottom we could just write as 5. So if you entered this in the calculator, it should be the same as entering this. All right, I'm going to go from the value I have on my notes here, which hopefully I entered this one right too, should be negative 419,430. Okay. All right, so this next one is pretty nasty. I'm going to go through showing you a method that just uses the formulas we already have, and then I will show you a new formula that could be used to solve this same problem. It makes it much easier. The drawback is you have an additional formula then to try to remember. Okay, so what we are giving here is, it says find the sum of a geometric series for which the first term is 15,625, the last term is negative 5, and we don't even know how many terms there are, and the common ratio is negative 1/5. So the big issue is if I want to use this formula, the S sub n formula, I have to know what R is, or sorry, what N is. I already know R, they gave me that, but I don't know how many terms there are. So if I'm going to use this, I've got to find N. So then you might be thinking, well, how am I going to find N? Well, we can use this because we know if it's geometric, A sub n equals A1 R to the n minus 1. And we already have A1, we already have R, and we have the value of A sub n. We just don't have the value of N. So if we plug everything in, A sub n is negative 5. A1 is 15,625. And R, make sure it's in parentheses, is negative 1/5. And that is raised to the n minus 1 power. So now we need to solve this. Well, we want to get the n by itself, ideally, so we're going to divide this over. So we end up with negative 5 over 15,625 equals negative 1/5 raised to the n minus 1. You could reduce the fraction. It reduces down to negative 1 over 3,125 equals negative 1/5 to the n minus 1. And here's where we might have an issue. So the ideal way to solve an equation like this, you're trying to solve for an exponent, you really want to use logarithms. But you may not have covered logarithms yet at this point. So we can solve it without knowing how to use logs. We will solve it by inspection. So what I mean by that is we're just going to keep picking powers until we find the power that makes this equation true. But we're going to try to make it easier to look at. So this is a pretty nasty fraction. This one converts to a decimal. If you put it in your calculator, it's going to give it to you in scientific notation. It's going to be negative 3.2 times 10 to the negative 4. And the way the calculator will actually write that is negative 3.2 e, indicating the scientific notation, negative 4. All right, so I'm going to say that's equal to the other side. And then I'm going to make one additional change. I don't really want to deal with this n minus 1. So for right now, I'm going to say let's let x equal n minus 1. So I could rewrite this equation as negative 3.2 e negative 4 equals negative 1/5 to the x power. Let's just figure out what x has to be, and then we'll go back and figure out what n is. And so the idea is we're going to just keep guessing. We're going to guess at values of x. We're going to plug numbers in until we get this out. So you're going to use your calculator to do that. Many ways you could do it. You could just manually type this in. But let's use the y equals. So if you go to y equals, we're going to type in negative 1 divided by 5 raised to the x power. And we're going to let it plug in numbers for us. So to do that, we're going to make a table. To make a table, you can hit second and then the graph button. You can see table above it. Okay, and this is going to plug in different exponents for us. And what we're looking for over on the y1 column, we're looking for this decimal here. And you're going to want to actually move the cursor over so that it's actually cycling down that column. And down here, we're looking for this exact number. And if you go down, you can see, bingo, we hit it at 5. Let me just pull that over. We can minimize this. So what this is saying is if the exponent is 5, then, and you plug 5 in right here, then the output will be this decimal. So x has to be 5. But I didn't want the x, I wanted n. So we can plug this back in here. That means 5 has to equal n minus 1, which means n is actually 6. Okay, so all that work just to find how many terms there were. Right? What we have found here is that 6 is the solution to that equation. It's a pretty messy process to do this, which is why logarithms would make it a little bit better, but it'd be better if we just had a completely different formula, which we'll look at in a second. Okay, but we're still not done. Now we need to plug everything into this. It wants the entire sum, so s sub n, which in this case is actually s6, it's the sum of the first 6 terms, equals A1, which was the 15,625, multiplied by 1 minus negative 1/5 raised to, now we can put in the 6 there, and that's divided by 1 minus a negative 1/5. Okay, let's actually type this one in the calculator, just because it is a little messier. All right, so back to the home screen. We've got 15,625 times, put your fraction in, and then 1 minus. Now, you don't need to use the fraction button within this fraction here. You can, but you don't have to. We can just use the regular divide button. So negative 1 divided by 5, just make sure it's in parentheses, raised to the 6th power over 1 minus negative 1 divided by 5. Hit enter on that, and we get our answer. So final answer for the whole thing was 13,020. Okay, that's a pretty messy process. So could we come up with an easier way? We can, but we're going to have to manipulate the sum formula. So this is the sum for a geometric series that we've been using for the whole set of notes, and we're just going to modify it slightly. So the first thing I'm going to do is I'm going to distribute this back through the top, multiply it by each term in the numerator, which takes us back to this form. The next thing I'm going to do is I'm going to look closer at this term. I'm going to pull off a factor of r from this, which is what I've done here. I've just pulled an r off, which means that the power then would decrease by 1. Right? This power, if it's n, if I pull one of the n's off, it's now, one of the r's off, the power is now n minus 1. If you multiplied these back together, you would add the exponents. The exponents on this is 1, so it would just take that power back to the nth power. Now, why would I do that? Well, if you look at what I've highlighted in blue here, that by definition is a sub n. That's the explicit formula for the nth term of a geometric series. So we could replace this just by a sub n. And notice this formula doesn't really use the value of n. I mean, you could say it's here, but we were given the value of the nth term in that previous example. So this will make the computation much easier. So let's solve a similar problem to the previous one. It's basically the exact same setup. I've just changed the numbers here. We want to find the sum of the geometric series where the first term is 1, the last term is this, and the common ratio is 3. Rather than finding the value of n, we can go straight to this formula. So we've got S sub n equals a1, which is 1, minus a sub n, which is this term, 19,683. Then we multiply that by r, so r is 3, and then the denominator would be 1 minus 3. And then we just have to enter that in the calculator. So according to my notes here, it should be 29,524. Much, much easier. Let's go back and see how it would have looked in the previous problem. Let's clean some of this up here. Okay, so again, that formula was S sub n equals a1 minus a sub n times r over 1 minus r. So for this problem, without doing all of this work, we could have just done 15,625 minus negative 5 times the negative 1/5, and then divide that by 1 minus a negative 1/5. So I'm going to leave it to you. You can try typing that in the calculator and verifying that it does come out as the same thing that we had before, that this came out to 13,020. Okay, this is another example. Oh no, this is different. So we are going to do something similar in this one, but we won't need that new formula. So we are still solving for a specific part of the sum formula. In this one, we're given the first term is 3. We're given the common ratio is 6. And we're given that the sum of all the terms is 4,665. So let's start by just writing the SN formula, the original one. So notice we have everything in this formula except the value of n. So when we solve this, it is going to be similar actually to the first method, the harder one, but the algebra here is quite a bit cleaner. So let's plug in. We've got 4,665 equals A1, which is 3. So I apologize for the buzzing. They're testing something on the announcements. So hopefully it stops soon. Okay, so we've got 1 minus 6 to the n, we don't know what n is, over 1 minus 6. That's everything plugged in. Now we just have to solve this algebraically. Okay, first thing I would do is I would deal with this 3. You could distribute it through the top, but I think it's going to be easier if we just divide it over. So we're going to do 4,665 over 3 equals 1 minus 6 to the n over negative 5. If this left-hand side does not divide nicely, then you need to leave it as the fraction. But in this one, it does divide out nicely. You get, I believe, 1,555. Okay, equals what we had over here. The next thing that I would do is I would multiply both sides by negative 5. So what you end up with then is negative 7,775 equals 1 minus 6 to the n. Okay, then we can subtract 1 over, so it's negative 7,776 equals negative 6 to the n. Both of these are negative. We could multiply by a negative 1, so we get 7,776 equals 6 to the n. Okay, at this stage, then we're going to finish it by either, if you know how to use logarithms, you can take a log of both sides, apply properties of logs to get your answer, which is going to be the quick way. If you don't know how to do that, then you can just solve it by inspection. We can just plug values of n in until we get the answer that we're looking for. So again, to review that process, go back to y equals. We're just going to put 6 to the x in there, and then we're going to go second table. And we're looking for when the y value hits 7,776, and we can see that it's when the x, or the n in this case, is equal to 5. So according to that, n has to be 5. 6 to the 5th power is that. So what we have found is, given this information, we know that there were actually only 5 terms in that sum, 5 different terms in the series that added up to this value. All right, just to make sure we have that process, let's do it one more time. We're given different information here. Let's write down what we know. We know A1 is equal to negative 4. We can find R by dividing 2 consecutive terms, so negative 12 over negative 4 is positive 3. 2 negatives cancel. And that's all we know. So then let's rewrite the S sub n formula. And we can plug everything in. So we've got negative 13,120 is equal to negative 4 times 1 minus 3 to the n over 1 minus 3. And we solve it using the same procedure as before. So we start by dividing over the negative 4. When you divide that over, you're going to get 3,280, dividing both sides by 4, and that just leaves the rational expression there. I guess I could go ahead and subtract these two, so you have a negative 2 there. To get rid of the negative 2, we're going to multiply both sides by negative 2, which gives you negative 6,560 equals 1 minus 3 to the n. Subtract the 1 over, negative 6,561 equals negative 3 to the n. multiply both sides by a negative to just have 6,561 equals 3 to the n. And then now either use logarithms or solve it by inspection. So again, let's review that one more time. Go back to y equals. This time it's going to be 3 raised to the x. Second table, and we're looking for 6,561, and we can see that's down when x was 8. So that means in this game we're using n here, so n has to be 8. There were actually 8 total terms. We stopped out at the 8th term to get the sum to be equal to negative 13,120. Okay, I'd say those are probably the most complicated ones. So let's finish by solving 3 application problems. All right, so the first one says, in the book Roots, author Alex Haley traced his family history back many generations to the time one of his ancestors was brought to America from Africa. If you could trace your family back for 15 generations, starting with your parents, how many ancestors would there be? So we've got ancestors. Let's just start writing out the sequence of them. So you start with your parents. You got 2 parents. Then we're going to add to that your grandparents. Well, each of your parents have 2 parents, so that means you have 4 grandparents. Then your great-grandparents, you're going to end up with 8 of those. So we can see what's happening here. It's doubling each time. So that means A1, your first set of ancestors would just be 2, and R, the common ratio, is also 2. We're trying to find the total. So the key is total, which means we're going to use the SN formula. So we want to go back 15 generations. Okay, so SN is A1 times 1 minus R to the N over 1 minus R, and we just plug everything in that we found. We're doing S15, sum of the first 15 terms of this, because you want the total. You just don't, you're not looking for how many are in the 15th generation. You want the total, all of them together. Okay, so we've got 2 times 1 minus 2 to the 15th over 1 minus 2. And if you put that in your calculator, you are going to get a very large number. So that comes out to 65,534 ancestors. Going back 15 generations, that's how far. Now, I'm not sure Alex Haley actually traced it back 15 generations because, man, that would be a lot of people to try to keep track of. But that's how quickly it grows. That's how quickly your family tree grows. All right, let's try another example. And maybe this is a little too soon for what's been going on in the world lately, but it is applicable. So this says contagious diseases can spread quickly, very quickly. Suppose 5 people are ill during the first week of an epidemic, and that each person who is ill spreads the disease to 4 people by the end of the next week. By the end of the 10th week of the epidemic, how many people will be affected by the illness? Okay, so the fact that it's spreading to 4 people, every time the next person spreads it to 4 people, that's what tells us this has to be geometric. The fact that we're finding the total number of people affected tells us that we're adding that geometric sequence, that we're doing a series here. So we know the initial amount was 5 people. Then the common ratio is 4, because each of these 5 people are going to spread it to 4 people, and they're going to spread it to 4 people, and it's just going to continue on like that. And we want to know if this goes on for 10 weeks, what are the total number of people affected? So again, back to S sub n, we've got A1 times 1 minus R raised to the n over 1 minus R. Okay, so we have 5 times 1 minus 4 to the 10th over 1 minus 4. And if you enter all that in the calculator, you're going to get a gigantic number. It is 1,789,569,705. And just to be sure, since that is so large, let's just double check. Let's type it in again, make sure I didn't type it in wrong. So we said there were 5 people initially. Hold on, let's do that again. 5 times fraction 1 minus 4 raised to the 10th over 1 minus 4. So let's make sure I got my commas there in the right place. Oh, I definitely typed something in wrong, didn't I? Okay, not nearly as big. I'm not sure where I'm getting those other ones from. I must have had I don't know. Okay, so it should have just been 1,747,625. Not nearly as big as this one. That was way off. But you can see it is still a very large number. So in just 10 weeks, it spread to almost 2 million people. Now, if you follow the news at all, you have heard about this concept. In the news, a lot of times with COVID-19, they talk about the R0 value. When they talk about R0, they are talking exactly about this. R0 is how likely it is for one person to spread, like on average, how many people do they spread it to? This is a giant R0 value. Most likely COVID-19 is not even close to this R0 value. We don't know the exact value, obviously. We just run statistical models to try to approximate it, and it's constantly changing. So I'm not even going to quote what they think it is here. But with most diseases, the R0 value is going to be less than 1. If the R0 is bigger than 1, then you have a huge problem. That's when things just blow up. But if the R0 is less than 1, then you will actually see the total number of people infected will actually max out. It will hit a maximum value, which is what happens with most diseases. Okay, last example. It says Rob is helping his dad install a fence. He is using a sledgehammer to drive the pointed fence post into the ground. On his first swing, he drives the post 5 inches into the ground. And then it says, since the soil is denser and the deeper that he drives, on each swing after the first, he can only drive the post 30% as far into the ground as he did on the previous swing. How far has he driven the post into the ground after 5 swings? Okay, so there's a lot going on here. It is still a geometric series, and that's because, each time it's 30% of the previous. So we're multiplying the previous by 30% to figure out how far he's driving it the next time. So what do we know? A1, the first hit of the on the post, it goes in 5 inches. Then the R value, what we're going to multiply each time, is 30%. So 30% as a decimal is 0.3. Remember, make sure we are converting those. 30% means 30 over 100, which means you move the decimal place back 2 times, so that is 0.3. You have to change that to the decimal value. And we know we're driving the post in with 5 swings, so N is also 5. So then we can go straight. We want to know the total distance that it's been driven. It says how far has he driven it after 5 swings? Not on the 5th swing, but the total after 5 swings. That's why we're using SN. So we've got A1 times 1 minus R to the N over 1 minus R equals 5 times 1 minus 0.3 raised to the 5th power over 1 minus 0.3. And you enter that in the calculator, so I'm hesitant to use my notes here. We'll test it, I guess, but my notes say this, 7.1255 inches. Let's double check that on the calculator. Try that again. Okay, not having much luck here. 5 times fraction 1 minus, and you can just do 0.3, you don't have to put the 0. And it was to the 5th power over 1 minus 0.3. All right, so that one did match. All right, so total number of inches after 5 swings is a little over 7 inches. All right, I believe that completes the notes for this section, so hopefully this is helpful. If you're having any problems with any of the with the assignment, then make sure you are contacting your teacher.